Welcome to a new module, Instruction Set Architecture and CPU Organization. We've talked about number systems, computer arithmetic, ALU. Now we are going inside the brain. We are talking about instruction sets. In Module 1, we got to know that a basic CPU instruction is just a command. It's a pairing of an opcode, which is the action to perform, and operands, the data on which the action will be performed. But here is the billion-dollar question that defines the entire personality of a processor. How many operands can one instruction handle? Can I say add A, B, and C? Or can I only say add A and B? This seems like a small detail, but it forces a painful trade-off between hardware and software. Here is the battle. First, the instruction length or hardware cost. If you want an instruction to handle lots of operands, your instruction binary becomes huge. It takes up more bits. This makes the CPU hardware complex and expensive to build. And another is code length or software cost. But if you limit the operands to keep the hardware simple, you need more instructions to do the same job. Your program file size gets bigger and it might run slower. So, do we want a complex hardware with short code or simple hardware with long code? To decide, we have to look at the four classic formats: 0, 1, 2, and 3 address instructions. And to compare these fairly, we are going to make all four formats solve the exact same math problem. Y equal to A plus B times the quantity C plus D. We assume A, B, C, and D are memory addresses, and we have CPU registers like R1 and R2 available. Let's see who does it best. First up, the 3 address format. I call this the rich kid format because it has room for everything. It specifies 3 distinct locations, 2 for the source data and 1 for the destination. The format is opcode, destination, source 1, source 2. For example, add destination, source 1, source 2. And the operation is like the addition of source 1 and source 2 will be stored as the result in the destination. This is incredibly powerful because only a single instruction can perform a complete operation, and this format results in shortest code. And most importantly, you can perform a complete math operation without destroying your original data. But the instruction binary is very long, and the CPU's instruction decoding and data fetching logic is more complex. Now, let's solve this arithmetic expression. Since we have 3 slots, we can do this very cleanly. Step 1. We need to add A and B. So add R1, A, B. This puts the result of data in memory, address A plus data in memory address B, into register R1. Step 2. We need to add C and D. So add R2, C, D. This puts the result of data in C plus data in D into register R2. Step 3. Now multiply the 2 results. So multiply Y, R1, R2. This multiply R1 and R2 and save it to memory location Y. So, as you can see, total instructions here are just 3. This is the shortest code possible. It is clean, easy to read, and we didn't touch the original values of A, B, C, or D. So why don't we use this for everything? Look at the hardware cost. If an address is 32 bits and you need to fit 3 of them into one instruction, that is 32 times 3 equal to 96 bits just for the addresses, plus the opcode. This creates a very long instruction. The CPU needs complex decoding logic to handle this massive command. So, what if we can't afford that complexity? What if we only have room for 2 addresses? That forces us to change our strategy completely, and that is what we will see next. Now, let's look at the 2 address format. This is the compromise. It is historically the most common format used in your classic Intel x86 chips. The format is opcode destination source. For example, add destination source. And the operation is like the addition of destination and source will be stored as the result in the destination. And here's the catch. Notice something? One of the locations does double duty. It acts as a source and a destination. This makes the instruction shorter, which is good for hardware, but it is destructive. If I say add A, B, I'm overwriting the value of A with the result. If I needed A later, too bad. It's gone. So one of the original data here is changed. So how do we solve our equation without destroying our data? We have to pay a tax. We have to use extra move instructions to save copies of data first. Step 1. We can't just say add AB because that destroys A. So first, we copy A into a register. Move R1 A. So now register R1 has the data of A. Then add R1 B. Now R1 has A plus B. Step 2, same thing for C and D. Move R2 C, add R2 D. Now register R2 has C plus D. Step 3, multiply R1 R2. So R1 holds the final result. And then move Y R1. Save the result to memory location Y. Finally here, you can see the total instructions are 6. We doubled our code length compared to the 3-address format. Why? Because we had to waste time moving data around just to avoid destroying it. Now, let's strip it down even further. What if we only have room for one address in the instruction? This creates the accumulator architecture. The format here is opcode address. But wait, where is the second number? Where does the result go? Actually, it is implicit. There is a special VIP register in the CPU called the accumulator or AC. Every single operation must happen inside this register. For add X, the operation is like, the data in X is added to the data in AC and the result is stored back in the AC. Think of an old calculator. You type a number, hit plus, type another. The screen, or here the accumulator updates. You don't tell the screen to update, it just does. Let's write the code. This is going to be painful because we only have one hand, the accumulator, to hold things. Step 1. For the first bracket, first we have to load the data of A into the accumulator. So load A. Then add B to it. So add B. Now AC has A plus B. Then we need to calculate C plus D. But the accumulator is holding our first answer. We have to empty it. So we save the result to a temporary spot in memory, T. Then step 2 for second bracket. Now the AC is free. So load C, add D. Now AC has C plus D. Now step 3 to multiply and finish. Now multiply by that temporary value we saved earlier. That's why multiply T. So AC has the final result. And finally, store Y. So here total instructions are 7. And the verdict is that this is hardware simple but inefficient. Everything has to funnel through that one accumulator bottleneck. And look at all those loads and stores. We are constantly talking to memory, which is slow. So we went from 3 operands to 2 to 1. Can we go lower? Can we have 0 operands? Can we write an instruction that is just add, no arguments? No registers, just add. Believe it or not, yes, that is the 0 address instructions. The format is just opcode. Just add, no A, no B, nothing. How does it work? It relies on a data structure called a stack. Think of a stack of plates in a cafeteria. You can only do 2 things. Push when you put a plate on top, and pop when you take the top plate off. Here, all operations implicitly happen to the top 2 items on the stack. The rule is, when you say add, the CPU automatically pops the top 2 numbers, adds them, and pushes the result back on top. To solve our equation, we use a different way of thinking called reverse Polish notation, or RPN. We load data first, then operate. Step 1, push A, push B. Now the stack has A and B on top. Then send the command add. Now the hardware pops A and B, adds them, and pushes the result A plus B back. Step 2, now in same way, push C, push D. Then send the command add. So now The stack has C plus D on top and A plus B underneath it. Step 3. Now we have our two bracket results on the stack. So multiply. Here the hardware pops both, multiplies, pushes final result. Finally, save it to memory Y. So pop Y. And here the total instructions are 8. So the verdict is that it forms the most compact code. And the CPU logic is simple. But it's hard to manage. It's difficult to access data in the middle of the stack. And pushing and popping for every operation can be slower than using registers. So let's look at the scoreboard. 3 address, 3 instructions. 2 address, 6 instructions. 1 address, 7 instructions. And 0 address, 8 instructions. Now, you might ask, which one does my iPhone or laptop use? The answer is none of them exactly. They use a modern hybrid. Modern chips, like the ARM chip in your phone or MIPS or RISC-V, realize something important. Registers are fast. Memory is slow. So, they use an optimized 3-address format. It looks like the rich kid format, add R1, R2, R3. But there is a strict rule. Math operations can only happen on registers. You cannot add directly from memory. If you want to add A and B, you must explicitly load them first. This is called load-store architecture. This separates the heavy lifting math from the logistics of moving data, making modern CPUs incredibly fast and efficient. So, we have decided on the logic of our processor. We know if we want 3 operands, 2 operands, or a stack. But this leads to one final massive physical design question. If I have a complex instruction, does it take up more bits in memory than a simple instruction? Should every instruction be the exact same length like 32 bits is? Or should we let some be tiny and some be huge to save space? This is the battle of fixed length and variable length instructions, and it decides how your CPU actually decodes the binary. That is our next topic. Hit subscribe, and I'll see you there.